Hey, so this is Joe, and this is the fourth video of the 12th chapter of Stewart's Calculus, and we're going to be talking about lines and planes in three-dimensional space. So, first off, let's look at a picture that's taken from your book that kind of shows how lines are to be described. Then I'll talk about the three kind of forms in which we can describe a line in three-dimensional space. So, come over here. We've got line L running like this, and we describe line L in terms of vectors. And so this is kind of where in the couple of videos ago when I said in three dimensions think about points as vectors that start at the origin and have the terminal point is the point we're talking about, and that kind of comes in handy here when we start describing lines, because we describe them in terms of vectors, but those vectors we can also think of as points. So what we need in order to describe a line, we need 2 points, or 2 vectors, and those 2 points must lie on the line. So in this case, we've got P0, which is the terminal point of R0, and so that's kind of an initial point, you can think about it that way, and it needs to lie on L. So in this case we've got P0 or the vector R0, and really we say R sub 0, P sub 0, we're talking about the same point, just with R sub 0 we're talking about it in terms of a vector that starts at the origin, and so that means that we can do vector operations with it, and that's ultimately how we're going to end up describing this line. And so that's going to be P sub 0 and then P, which is just generally any point on the line. And you might say, well, how do we know that that's any point on the line? Well, it's because P, or vector R, its components are x, y, and z, which are all variables, whereas R sub 0 is described as just one point, because x sub 0, y sub 0, and z sub 0, these are all definite points. These are all integers. Or they don't, I guess they don't necessarily need to be integers, they can be any number, but they're real numbers, whereas, and they're actual values, whereas x, y, and z, those are variables that generally describe this line. So we need those two things. We need our initial vector that's a point, and we need our other vector that we can think of as a point, but it's really the whole set of points that make up the line. And then we also need a vector v, and this vector. And the important thing about this vector is it determines the direction. Of line L. So vector v is always going to be parallel to L. So it's going to be in the same direction. And most often this will either be some vector that you're trying to find a line parallel to, or a unit vector that will just broadly describe a direction, and we don't really care about the magnitude too much. So these are the three things we need. We need one point on the line, a defined point on the line. We need generally all the points on the line, and so that's always going to be the same thing as P, X, Y, and Z, because we're going to be describing this line in terms of x, y, and z, because we're using a Cartesian three-dimensional plane. And then we need a vector that describes the direction of this line. And so now that we have those three things, we can actually start describing this line. So what we need to do is we want to find a vector that actually lies on line L. And in order to find that vector that lies on line L, what we need to do is we can get this vector by doing the operation R, vector R, so we'll be able to find, and so vector A is a vector that lies on vector L, and we can get to vector A through vector V. Vector A is equal to vector V times some parameter t. So basically that's just a shift of V. And so that's how we're going to get to A, which is the vector that lies on L. But remember, we're trying to generally describe all points of L, not just one little vector on L. So we have this equality. So let's try to put A in terms of R and R sub 0. Well, we can do some vector addition. We find that R is the resultant of r sub 0 plus a, right? We have the tail to tip method going on here. R sub 0 plus a is equal to r. Well, we've defined this relationship here that a is equal to just a shift in v, so we can write that r is equal to r sub 0 plus t v. And that t in there, because that's a general parameter, that will allow us to describe all of the points in line L, and the fact that we have an r here, and remember this r corresponds to these three variables right there. Once we plug those three variables in for r, we'll be able to have a general equation in terms of a general parameter t for all of the points on line L. So this is kind of the base way of our first form for describing all the points on some line in three-dimensional space. And then we have two sort of derivative forms that come out of this that I'm going to show you on the next screen. So here's the form that we just derived. We have vector r is equal to r sub 0 plus tv. And remember, r sub 0, that's our definite point that lies on the line. R represents all variables for all the points on the line. T is a general parameter, can be all real numbers. And v, that looks a little bit like an r. V is a vector that determines the direction of line L. So our second form for describing line L is we're just going to write out all these vectors in bracket form and perform this addition and the scalar multiplication here. So our r, that's x, y, and z, that's all three variables, is going to be equal to x sub 0 plus ta if we define vector v as being a, b, c. Y sub 0 plus tb, z sub 0 plus tc, and we can actually expand this into three different equations by just getting x is equal to x sub 0 plus ta, y is equal to y sub 0 plus tb, etc. So that actually is three different equations, and all three of those equations will describe line L, the sum of them together, all those parametric equations. But if we want to get rid of the parameter t, we have this handy we get down to this handy third form for describing the line, which doesn't have parameter t and it still describes the line just as well as these two other functions. And it's very helpful if we don't want a parameter. And that's x minus x sub 0 over a is equal to y minus y sub 0 over b, which is equal as well to z minus z sub 0 over c. And so this is a nice formula because we can learn a lot about a line, and it's very powerful if we only need to know two things. We need to know a point on the line, and we need to know a vector that determines the shape of the line. And that's it. We don't need to know anything about the parameter for that line. And since all of these are equal to one another, if we don't have information on one of the components, say, of the point that lies on the line, or one of the components of the vector parallel to the line, then we can figure that out because these are all ratios and they're all equal to one another. So that's kind of it for the forms for describing a line. Now let's talk about the forms that we can use to describe a plane in three-dimensional space. Alright, so now we're going to talk about describing a plane in three-dimensional space. So a plane is basically a set of points in space that don't have any depth. It's just one set of points that's only 1 point thin, if that makes sense. It's a set of vectors. You can think about it also as a set of vectors kind of coming out of one another. But an infinite amount of vectors, right? So the first way, so all we need to do to describe a plane is we need 2 points in the plane and the normal vector to the plane. And so a normal vector, which is this vector n right here, that normal vector is binormal to any two vectors in the plane, and it's orthogonal to any vector in the plane, and we say that it's perpendicular to the plane itself. And so this is the main thing that we need to describe the plane. But we also need two other vectors. We need an r sub 0, and this r sub 0 goes from the origin to the point P sub 0, which is x sub 0, y sub 0, and z sub 0. And this is going to be a defined point. That's a defined point, sort of like describing a line. It's the same deal. Those are all going to be numbers in there. And P sub 0 is important because that is the point at which the normal vector starts. So that's a very important point to know. The second point that we need is the general point x, y, and z, which are all the variables that describe all of the points in the plane. And P is the terminal point of R. So once again, we're thinking of points as vectors that start at the origin. So really all we need is R sub 0, and n in order to describe a plane. And so the first thought we should have is, well, when we describe the plane, we're going to be describing some sort of orthogonal relationship between n and those two vectors. However, one vector has its terminal point at the base of n, and one has its terminal point, well, at all points on the plane, because generally it's described by these variables. However, we can do some vector subtraction and get an r minus r sub 0, which has its first point at the same first point as n, and it lies in the plane, so it's going to be orthogonal to n. And what's an easy way of describing orthogonality? Well, by using the dot product. So we have this relationship where the dot product between n and r minus r sub 0 is going to be equal to 0, right? And when we expand that out, and let's say that n, we're going to generally describe that as a, b, c, that vector, we get this relationship that a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 is equal to 0. And this is the general form of for describing a plane, and that comes out of this dot product, right? We just performed a dot product right there. And so that is generally how we describe a plane when we have our general point, the point at the base of the normal vector, and the normal vector itself. However, so using that, I'll show you the three kind of general forms we can use to describe a plane. So we've got our dot product notation here, and we don't use that very often. And then we've got the expansion of that dot product notation, where we explicitly say where the point at the base of the normal vector is, right here. And then if we were to basically distribute in each of the components of the normal vector here into these subtractions, we'd get the sort of more condensed version of expressing a plane, where we get some constant d that's being added to the ax, by, and cz here. But nonetheless, we're always going to be setting this equal to 0 because of the orthogonality described by this dot product. So this is all fine and dandy if we know where the normal vector starts, and we know what the normal vector is. But normally, when we're trying to describe a plane, we only know a couple points that lie in the plane. So how do we deal with that? How do we deal with just knowing a couple points in the plane? Well, really, ultimately, what we're going to try to do is get to a place where we'll be able to describe a normal vector based on those 3 points. So we come back over here to our plane, and let's say we only know a point. We just know 3 general points. We know this point right here, we know some point out here, and some point out here. Well, and say we don't know where the normal vector is coming out of. That's okay. When we have just 3 points to describe a plane, we get to choose where the normal vector comes out of. And so we'll define one point. We'll call it P sub 0, and this will be P sub 1 and P sub 2. And alternately, we can call them, in vector notation, R sub 2, R sub 1, and this would be, again, R0. And so let's say we have these 3 arbitrary points. We arbitrarily say, okay, this p sub 0, this one right here, that's going to be the base of our normal vector. And then so what we need to do is we need to define, and I'll draw out these vectors here for you to kind of make this a little bit more explicit. What we need to say is, alright, we know that the normal vector is going to be orthogonal to the plane. And what's a way of describing orthogonality? Well, if we have any two vectors connected to one another, their cross product is going to be orthogonal to both of them. It's going to be binormal, right? So what we need to do is we need to describe a vector like this that connects point P0 and point P2, and also connects point P0 and point P1, and then find the cross product of those two vectors, and that'll give us the normal vector. Well, this vector right here is going to be r sub 2 minus r sub 0, and the one connecting r sub 0 and r sub 1 is going to be r sub 1 minus r sub 0. And so you take the cross product of r sub 1 minus you take the cross product of r sub 1 minus r sub 0, you cross that with r sub 2 minus r sub 0, and you will get the normal vector. And actually, it doesn't matter which order you do this cross product in. We're going to do a sample problem later to prove that it doesn't matter which order you do this in, but that is generally how you should go about solving for the form of a plane. And then once you get this normal vector, you have your r sub 0, and you'll be able to put it into that form of the plane that we were talking about earlier. But generally, this is the form for finding that expression if you only have 3 points that are coplanar to one another, that lie in the same plane. And if you have trouble remembering this graphical interpretation, all you need to know is you arbitrarily define one of your points and do one point minus that point, cross product with the other point minus that same point, and that will be your normal vector. So now let's let's go do some practice problems with that involve using the form of the line and the form of a plane. Alright, so we're going to do number 5 on page 848 in your book, and the question asks us to find the line through point 1, 0, 6, and that's perpendicular to the plane x plus 3y plus z equals 5. Okay, so first we need to figure out what we know and what we need. Remember, we need a vector that's going to be parallel to the line, and that vector is going to be a vector v. So we need a v, and we need an r sub 0 that is some defined point on the line x sub 0, y sub 0, z sub 0. So we already have that point on the line, because the line needs to go through this point right here. So our r sub 0 is going to be 1, 0, 6. And now we need our v. And our v, so we need to say, okay, it's going to be perpendicular, the line is going to be perpendicular to the plane, this plane. Can we find a vector that's perpendicular to that plane? Yes, the normal vector. Remember, the normal vector is always going to be perpendicular to our plane. So our v is going to be the normal vector, and the normal vector is some a, b, c. And how do we find the normal vector out of this plane? Well, remember, the general expression for a plane is ax, or one of them, by plus cz plus d is equal to 0. The d we don't care about, that's a constant, but our a, b, and c, those are the components of our normal vector. So all we need to do is look at the coefficients of x, y, and z, and we'll be able to find our normal vector or our v. Because remember, the normal vector is always perpendicular to this plane, and we want our line to be perpendicular to that plane, and so our line needs to be parallel to n, or v. We're talking about the same thing there. So our a is going to be 1, our b is going to be 3, and our z is also going to be 1. So now we can start plugging in for our general form of a line. So let's write that down. Our r, which is going to be x, y, and z, are 3 variables, 3 Cartesian variables, is going to be equal to r sub 0 plus t v. That's actually going to be equal to r sub 0 plus t n, since we're using the normal vector for the plane. So we can start plugging in. Our r sub 0 is going to be 1, 0, 6, because that's the point that our line needs to go through. And that's going to be equal plus our parameter t times our normal vector, and our normal vector is 1, 3, 1. And that is going to be equal to x, y, and z. And now you can expand this out and write it in whatever form of a line you want, but this equation right here describes our line L that goes through point 106 and is perpendicular to this plane right here. So we're good. That not a very difficult problem to solve. You just need to be able to remember how to find the normal vector of a plane, and remember that the normal vector of a plane is always perpendicular to that plane. So let's go do one more problem here. Alright, so now we're going to do number 31 on page 848 in your book, and it asks us to find the plane that goes through points 0, 1, 1, 1, 0, 1, and 1, 1, 0. And so the two things that we need to find the equation for a plane is some r sub 0, which is going to be equal to some point, the point at the base of the normal vector, described as x sub 0, y sub 0, and z sub 0. And then we're going to need our normal vector, a, b, c. And the r sub 0, remember, is the base of that normal vector, and it lies on the plane. However, we have our 3 points. We have only 3 points right here. And remember, we can use the cross product of a vector that connects those two vectors that connect those 3 points to find the n. And since we only have 3 points, we can arbitrarily decide which point is going to be our r sub 0. And so we just need to define one. So I'm going to say, let's make our r sub 0 1, 0, 1, like that. And so then we're going to define an r sub 1 vector that goes from the origin and terminates at a point. We're going to make the terminal point of r sub 1 0, 1, 1, and this is completely arbitrary. You could do this a different way and you'd still get the same answer. And we're going to define our r sub 2 vector, which is just terminates at another point that lies on the plane, and define that as 1, 1, 0. So now what we need to do is we have our 3 points, and we need to connect them, and we need to connect them using some vector subtraction. And since we've defined an r sub 0, which is going to be the base of the normal vector, and the normal vector is the cross product of two other vectors, we need that r sub 0 to be the base point for the two vectors connecting r sub 0 and r sub 1 and r sub 2. So we're going to need to do some vector subtraction, where we take r sub 1 and subtract r sub 0 from it, and then we can cross that with r sub 2 minus r sub 0, and that's going to give us our normal vector right here. So let's first do this vector subtraction really quick. So r sub 1, we do a 0 minus a 1, that's going to be a minus 1. We do a 1 minus a 0, that's going to be a 0. We do a 1 minus a 1, that's a 0. Cross with, and now we do r sub 2 minus r sub 0. 1 minus a 1 is a 0. 1 minus a 0 is a 1. And 0 minus a 1 is a negative 1. And so this is all still describing our n. So now we're going to use our determinant talk here, our matrix talk. Get ijk, we get a negative 1, 1, 0. 0, 1, negative 1. And later on I'm going to prove that if we had crossed these two the other way around, for example, have r sub 2 minus r sub 0 first, we'd still get the same answer. And so that's going to be equal to, we do a 1 times a negative 1, that's going to be a negative 1 minus a 0, so that's just negative I, and then j, that's going to end up be a minus, and then a 1, and then minus a 0, so that's going to be negative j, and then the k, we're also going to get a negative 1 minus a 0, so that's going to be a negative k, and that is just going to describe our normal vector, and we can write that in bracket notation. That's going to be a negative 1, a negative 1, and a negative 1 is our normal vector. And so now we've got everything we need to describe this plane. We've got our normal vector, and we've got our r sub 0, which is the base point of that vector. So we can write out our form of a plane, which is a times x minus x sub 0 plus b x minus sorry, not x, y minus y sub 0 plus c, z minus z sub 0 is equal to 0. And so we start plugging in. We're going to get a negative x minus 1 plus, and now this b is going to be a negative 1, and that's just going to be a negative y, and the c is also going to be a negative 1. Oh wait, so yeah, we don't need that plus, and that z is going to turn into a negative 1. Sorry. So that's going to be minus a z minus 1, and that's going to turn into a 0, and so we kind of expand all this out, and we're going to get a negative x, negative y, negative z, and this is going to be a negative and a negative is a positive, so that's going to be plus 2, and we can bring that 2 over, and that's going to be a negative 2 right here. So this is going to be our plane. Now, I was talking, yeah, and so let's go look at that plane over here. So this is our plane. Negative 2 is equal to negative x minus y minus z. And so now we were talking earlier about if we had crossed those two vectors in another way, would we have got a different answer? And the answer is no. We would get the same answer, because we would get that our normal vector is equal to 1, 1, 1, 1, 1. Sorry, some technical difficulties here. So that would be our normal vector if we cross them the other way. And then let's just see what happens when we put everything into our form of the vector equation. We'd get x minus 1 plus plus y plus z minus 1, sorry, is equal to 0, and then that would end up being x plus y plus z is equal to 2, and the only difference between this equation and this equation is that everything is multiplied by a negative 1 right there. And so does that make a difference graphically? And again, the answer is it doesn't, because let's look at 2 is equal to x plus y plus z, and put an equal sign there, and we get the same plane. Look, it's the exact same plane. So my point is it doesn't matter which way you cross those two vectors. In the same way, it doesn't matter which point you choose to be your r sub 0. So that's it for this video talking about planes and vectors in three-dimensional space. I hope that it was helpful, and stay tuned for the rest of this course, because this finishes out chapter 12 then. So stay tuned for chapter 13. Thanks.